Hey guys, it's Booth Dog here. Um, I'm doing well. I hope every single one of you is also. I hope you're doing well. Your families are well. I hope everyone is safe. I hope you're staying safe, staying in, not going out. I hope you're getting everything you need. Um, these are interesting times. I know you might be feeling anxious, unsure. Very normal. We're all feeling that too. Um, But just know that there's a lot of work going on behind the scenes to continue to make sure that all of you are going to get the best education opportunities as humanly possible. Um, I think crises like this tend to reveal a lot about who we are as people, as a community, as a school. Um, and so you're learning a lot about your teachers, you're learning a lot about each other, your family. Um, I think you're going to get the chance over the next couple of weeks, hopefully just a couple of weeks, to see a different side of your teachers. I'm not wearing a tie. I'm wearing my BB-8 shirt. You're going to see us a little more relaxed at times, I think. That's good. Um, just know that we're also working pretty diligently. Okay, so in a second, this is going to transition. You are going to hear a lecture not from Booth Dog, but from Mr. Boothman. And he's going to tell you all about today's lesson. We're working hard, and that means you do need to work hard as well. Okay? This isn't going to work if your teachers are the only ones putting in the time and the effort and the energy to this. Part of it needs to come from you, and that's fantastic training for college and what college is going to be like. Very self-directed, very self-disciplined. Are you checking in on the things you need to check in on? Are you doing things without being reminded 20 times? These are really good skills for you to develop, and I think that is one good that can come from this. But it's going to reveal which of you don't have those skills, which of you don't want those skills. So I genuinely hope that you're taking this seriously. I hope that you enjoy Mr. Boothman's lesson. As dry as it can be at times, I do apologize. But keep it up, do your best, stay safe. Here we go. All right, let's go ahead and jump right in. I have posted your blank Unit 7 guided notes packet, so hopefully you, even if you can't print it, that's fine. Just try to follow along. It would be best if you could print it, but I also recognize that it's kind of long, so do what you can. We're all being flexible. Very interesting time. Don't worry too much about it if you can't actually write on it, but do try to take some notes somewhere, whether that's in a separate notebook, separate paper, just something. The act of writing will help you quite a bit. Looking at where we have been so far this year, we are pretty close to the end. Like I told you before break, these last few units are pretty straightforward. They should each only take us a couple of weeks or so. So don't worry about like getting to finish everything. We're gonna be fine. And you can see right there what our next topic is. Before we jump into that, though, I do want to clarify one other thing. There were two last learning targets in Unit 6, 6.4b and c. I've decided that, especially with everything that's going on, those aren't essential. So for juniors who are in this class, we'll be talking about that during and after the seniors take their exams, which of course are a little earlier than yours. So go ahead and look forward to that. Seniors, I'm more than happy to talk about those with you separately, but don't worry about it. It's not going to be on your final. I'm not going to test it otherwise. They're more of, interesting little side notes about polar coordinates and complex numbers. Let's go ahead and jump in and talk about vectors. Okay, that is our topic for Unit 7. What is a vector? I really want to give you some time to think about what a vector is. I'm sure we all have some idea in our head, of course. So I'm I'm sure we're all thinking something like that, hopefully. And indeed, this is a vector, a very basic vector. But what makes a vector a vector? Okay, there's a lot of vocab that we're going to introduce throughout this unit. Don't worry, it should all be fairly straightforward, but try to follow along. Okay, I'm going to post this link to this lovely little YouTube video. I'm sure once you open it, you'll see why I enjoy it so much. It gives you a great idea of what a vector is. So if you want, take a second, pull that up, pause this video, open that up, watch it. It's like a minute long. Come back to this and be ready to jump back in, and we'll talk about what a vector is. Okay. All right, so you watched that video. Hopefully you saw what is a vector. Okay. It's that arrow that shows up on the boulder that Link is trying to throw somewhere. And you'll notice that that arrow is getting larger the more Link hits the boulder. Okay. And it's also changing direction depending on how he's hitting the boulder. Okay. These two components are what makes a vector a vector. Okay. So to talk about vectors, we need to take a step back and talk about what's known as a scalar. A scalar is a measure of magnitude. Okay, measure of magnitude. So examples of scalars, there's quite a few of them. Okay, we can talk about something's weight. That's a scalar. Okay, we can talk about something's length. Okay, we can talk about temperature. We can talk about area of something. Okay, magnitude is just a quantity. It's an amount. So anything you can have an amount of, we can think of as what is known as a scalar. Okay, now a vector tells us the magnitude of something. So we do have this scalar component to it, but it also tells us the direction of something. Okay. So easiest explanation I can give you, easiest example I can give you is something's velocity. Anyone who's taken physics in any way knows that velocity, okay, is both speed, which is a magnitude, and direction. Okay, so velocity, it's not enough to just say we're going 60 miles an hour. We also have to be a vector, to talk about that velocity vector, we have to also specify what direction we're traveling in. So we're going 60 miles per hour east on the 10, okay? Or we're going 40 miles per hour north on Tyser Road. Okay? So that is really what makes a vector, those two pieces of information. Two vectors are considered equal if they have the same magnitude and direction. Okay, so that goes in those next two blanks. And we can also think of a vector as a measure of, here's your physics word, and it's something that will show up a lot next year in calculus, displacement. Okay. So if we're talking about motion, okay, I'm going to go back to velocity for quite a bit of this unit because it is our most straightforward example. If we talk about displacement of me and my car as I'm driving somewhere, okay, that is how much I've moved from one point to another. Okay, that amount is our vector. Okay, that's what our vector measures, not just how much I've moved, but where I have moved. Okay, very important. Okay. And before I skip past that, the zero vector, denoted by just a zero, okay, represents no displacement. Okay, so we're calling the zero vector a vector that equals zero. No change in our position, no change in where we've gone or how much we've moved. So we define a vector by two pieces, okay? And we use these weird brackets. They're like pointed arrows. They're literally called pointed brackets or angled brackets. And two pieces of information to talk about a vector. A is the horizontal component. B is the vertical component. Hopefully you see why we're talking about this after talking about trig, okay, and our complex numbers. We also had an A and a B for our horizontal and vertical components. Okay. Now looking at a graph like this, if I want to draw the vector 4, 8, then I'm going to go over 4. Now this is our horizontal component, and This is positive, so we're going to the right 4 units. And then I'm going up. Again, it's positive, so that's up 8 units. Over 4, up 8. So this right here is our vector v. Again, we had our horizontal and vertical component. One very special thing about vectors is that it didn't need to start at this point. Vectors, as a measure of displacement, do not have to start at the origin. As long as we're moving this amount to the left or to the right, and this amount up or down, we could have started literally anywhere in our coordinate system. Okay, so we could have started here. And as long as I'm going over 4 and up 8, there's our vector. Over 4, up 8, horizontal and vertical components. Okay. So, should still be pretty straightforward. Okay. So now we're going to talk a lot about what can we do with vectors. The rest of this unit is really how are we going to use these vectors, how can we apply them to different situations. But for now, we're really just going to stick to the basics with vectors. So we have what's known as component form of a vector. Okay, so component form of a vector, this is what you're filling in right here, looks like this. So given 2 points, if we're told that this vector starts at this point, where this point is x1, y1, and it ends over here at this point, and this point is x2, y2, then we need the change in horizontal position, okay, which is going to be x2 minus x1, and then we need its change in vertical position, y2 minus y1. And this is how we would get horizontal and vertical components for our vector. So very straightforward formula. Hopefully you see we're just calculating distance between our 2 points, breaking that up to talk about horizontal and vertical pieces, components. Okay. Let's look at our example. Find the component form of a vector u with initial point 1, 2, and terminal point 10, 8. Probably should have left myself a little more room on this coordinate system. All right, so here's our vector. This is vector v. Oh, I'm sorry, vector u. Typically use the letters u and v for most vectors, just like we use the letter z to talk about complex numbers and so on. Now, we want to write what is this vector's component form. Okay, well, we have its 2 points. So this vector is just going to be y or x2 minus x1, so 10 minus 1, and that's going to give us its horizontal displacement, its horizontal component, and then we have y2 minus y1. That's going to give us its vertical displacement, its vertical component. So this vector is actually just equal to 9, 6. And if we counted, we would see we're going over 9 and up 6. Again, this is positive, so we're going to the right. This is positive, so we're going up. Okay. Very straightforward. I'm going to kind of breeze through the rest of these operations. Hopefully they're not too tricky for us. Now, what if we want to find this actual distance here? Well, we have what's called the distance formula, and it's actually exactly what we're going to use. Now, we can also think of that distance by a few other names that we've used recently. We can think of that as our hypotenuse, as the absolute value if this were a complex number. Okay. But we're talking about a vector. We want that actual length of the vector, so we're using the special term magnitude of the vector. And how do we find that distance? It's the Pythagorean theorem. And we use absolute value bars to talk about the magnitude or the length of a vector, because In a sense, it's the absolute value of the vector. So straight from the Pythagorean theorem, square root of a squared plus b squared. Okay, so using this, we should be able to calculate a, b, and c. Find the magnitude of each vector. So let's start with a. Magnitude of this vector, again, those absolute value bars, it's going to be the square root of a squared plus b squared. 2 squared is 4, negative 3 squared is 9, 4 plus 9 is 13. We can't simplify that. So the magnitude of this first vector is the square root of 13. That is the length of this vector if we were to draw it out. B. Vector v is 5, 0. Magnitude of vector v, square root of 5 squared plus 0 squared. Hopefully we can see. It's just going to give us 5. Why am I ignoring the negative square root? It's a magnitude, it's a length, it's a distance, it's absolute value. Just like before. And finally we have c. Vector w, we have some fractions here. Stop whining, Mia. Absolute value. Magnitude of vector w is the square root of 3/5 squared plus 4/5 squared. Now, Jacob, take your time. Don't make a mistake like you tend to in class. And we get the square root of 9 over 25 plus 16 over 25. It's the square root of 25 over 25, which is the square root of 1, which is 1. Okay. So, magnitude of a vector, easy calculation, easy formula, shouldn't be too difficult for us, hopefully. All right, breeze through the rest of this section. Now, we want to talk about adding and subtracting vectors. Okay, what does that mean? What does it mean to multiply a vector by something or to add two vectors together? If we think of a vector as displacement, as a change in where we are from this point over to this point, then vector addition and subtraction and multiplying it by a number becomes very straightforward. Okay, so if we have this displacement and we want to add this displacement, well, then we just have to do one displacement and then the other displacement. And wherever we end up is going to be the addition of those two vectors. So if we were talking about vector u plus v, then I'm moving along vector u, and then I'm being displaced by the amount from vector v. And here's where I end up. So what is our actual displacement in the end? It's from this point to this point. And this is what we call vector u plus v. If we talk about multiplying a vector by something, so say we have u, this vector right here, and I want to multiply it by 2. Well, then I'm moving this much, and then I'm moving this much again. So I'm literally just multiplying that length by whatever I'm multiplying by. It could be 2, it could be a fraction, and then I'm getting smaller, I'm being displaced less. It could be a negative number, as we see here. If we multiply by a negative number, it's actually flipping our direction. It's the same length, but we're moving in the opposite direction. If this is vector u, this is vector negative u. And so thinking about negative just being the opposite direction, a displacement in the opposite direction, then subtracting two vectors just becomes adding a negative vector. So let's do a bunch of practice, a bunch of examples here. Let's write down like our general formulas for this. So if we have vector u is a1 and b1, vector v is a2 and b2, and then we have some number c, it's just a scalar, something we're multiplying by, then vector u plus vector v. We add our horizontal components, and we add our vertical components. And that's going to be our final vector. Vector u minus v, a1 minus a2, b1 minus b2. Again, we're just adding the negative. And then if we want to multiply a vector by some scalar, think of it as just distributing that scalar in. We have to multiply both of its components by that number. So, knowing that, let's do some practice. U plus v. Okay, so we have vector u equals 2, -3, and this is a1 and b1. Vector v equals -1, 2. I'm going to call this a2 and b2. So vector u plus v is going to be a1 plus a2. That's 2 plus -1. And b1 plus b2. 2 minus 1, -3 plus 2. And there's the sum of our vectors. Okay. U minus v. So a1 minus a2. b1 minus b2. Minus negative is plus. And there's the difference between our two vectors. All right, I'm going to do one more here with you. I'm going to ask you to finish D and E yourself. Again, these answers are all in the completed guided notes packet, which is posted to Google Classroom. Okay, let's do 2 times u. 2 times vector u. So again, we're thinking of this as just distributing in our numbers. We have 2 times 2, 2 times -3. So this is 4, -6. Very straightforward. Again, by problem E, we're doing a bunch of different things at the same time. Just take your time, multiply by the scalars first, and then add or subtract your vectors. Okay. So please go ahead and pause the video if you need to, finish those problems, check your answers on Google Classroom. Okay, I do have these practice problems for you. So hopefully you can see this here. Let me center this for you. As you can see, I had planned to do this as a brain hand. I guess if you want to drag a younger sibling or parent over with you, you can certainly do this as a brain hand, but please just practice it yourself. Find the component form of the vector v that starts at this point and ends at this point. Again, it's finding the difference between our horizontal and vertical components. You're subtracting. Finding magnitude. Okay. Finding magnitude is just finding length. It's the distance from where we start, our initial point, to where we end, our terminal point. So distance formula, the Pythagorean theorem. And finally, our vector addition and subtraction and multiplication by a scalar. Okay, so again, pause it, take some time and work through this. Again, I can't really force you to do this. I will very likely turn some of these questions into a Google form for you to answer, for you to fill out. Just please go ahead and go through that. I might, well, have, sorry, I'm figuring all of this out along with you guys. This is really it for section 7.1. I think actually I'm going to write some very similar problems to this, create a Google form, and that is going to be your exit ticket for this section. Thankfully, this is an easy enough section that you should be okay doing it online. You know, there's not a whole lot of work I need to check. Either you know what you're doing and you're going to get the right numbers, or you're not. So I will clarify that once I post this, but please take care of that exit ticket. Again, a little more practice, so work through this. And you should be all good to go for your exit ticket. Okay, so pause it, zoom in on this if you need to, and then get ready for that exit ticket. Okay. So take your exit ticket. That's it for 7.1. This is performing operations with vectors. Okay, Nate, for the love of God, please check your work and don't turn it in right away. And we're done. So please, continue practicing. I'll post some practice like normal to Google Classroom. We will continue looking at vectors over the next couple of days. The rest of the sections in this unit genuinely are this simple. There's not a whole lot to think about. It's just a bunch of formulas that we're kind of used to by now. All right, that was it. I hope you enjoyed today's lesson. Again, I will be available to video conference on Google Meet from 11 to 12 today. As we go forward, I'll reevaluate that and see if there's better times, if I need to be available a little longer. But we're being flexible for now. Okay, so 11 to 12 if you have any questions you need to ask me. Otherwise, feel free to email me. You know, I try to respond pretty quickly, and we'll go from there. All right, so thank you so much. Wash your hands. Stop touching your face as I touch my face for this entire video. Be careful.